or hc by lambda. That is known as photon theory of light. So total energy which I am receiving is n times h nu, and that comes to a brings us to a point that the energy is quantized. I cannot have receive energy from light in any manner, right? Actually, the light which I'm receiving in terms of photons, so the total energy which I'm receiving will be integral multiple of the energy given by one photon, right? N times
Yes.
h. So energy is quantized, okay. And application of photon theory is the photoelectric effect. Got it? So what do you mean by
Yes.
photoelectric effect? What do you mean by photoelectric effect? Photoelectric effect, it is the phenomena of emission of electron from the surface of metal when the surface of the metal is what?
It's the photons are
The surface of the metal is irradiated by
yes.
a light.
Mm. So I can't hear you.
Yeah, it got disconnected. Yeah. So why I was asking that why do I need the light of certain minimum frequency? Why can't have any light being used for the photoelectric emission? What's the reason? Because the photon should have certain particular energy. Okay.
Yes.
It is just like pushing a table. If I am putting less force on the table will not move no matter how long I keep pushing. Got it?
Yes, sir.
Is it clear? Suppose if I try to push a table and with very less force, will the table move?
Yes, sir.
It will not move, right? So
Yes, sir.
it will not. It is not going to move because the force is not sufficient, right? Same is the
Mm.
case with the photoelectrons also. The electrons
Yes.
are.
Your screen is not shared.
Yeah, just a second. I'm sure. So electrons are not going to come out until unless I put the photons of certain minimum frequency. Is it clear? And what is that
Yes, sir.
minimum frequency is known as threshold frequency. Okay, nu naught. Or sometimes, so what is the minimum energy corresponding to that minimum frequency? That is known as work function, and the corresponding minimum energy photon which is required is h nu naught. This is the minimum frequency, and this is the energy of the minimum energy which need to be required to emit a photon. This is work function. Is it clear or not?
Yes, sir.
So I need to put the energy, certain minimum amount of energy, then only my photons are going to get released. Okay, and this phenomena is known as photoelectric emission, and it is known as the photocurrent. The electrons which you observe, they are known as photocurrent because they keep flowing. Okay, so now uh, let me give you one question. Let's first write the point. Suppose this is the surface of the metal, and you are having the light striking on its surface. Got it? The photons. So what is the energy of the photons? The frequency of the light is nu. It should be greater than u naught. Got it?
Yes, sir.
And only the photoelectrons will come out. Okay. And you have the photoelectrons coming out. So how much energy each photon is carrying? H into nu. Got it? As per the Planck's quantum theory, the energy carried by each photon is h multiplied by the frequency of the light. Clear? Do all
Yes,
energy,
sir.
do all energy will be transferred to the electron as kinetic energy, or will some will be taken by the electron?
Will be taken.
Some energy will be taken by the metal because the electron is not free. It is held by the surface of the metal, so some of the energy will be consumed. Got it? So H nu minus H nu. This is what work function. So this is the minimum energy required to remove the electron, and it is just like, suppose if I push something, some of the energy will be used to overcome the friction force. Got it? And the remaining energy will be transferred to that object, and that will be the kinetic energy. So total energy which I am supplying, energy of the photon. Okay, this is the energy of a single photon. Minus the minimum amount of energy which is needed, that is known as work function, or HU naught, or sometimes it is equal to psi phi naught. Okay, and that will be equal to that. Got it? Kinetic energy of the photon. Is this clear?
Mm.
So this is, so if you put less amount of energy, okay, you are not going to see the emission of photoelectrons. Let's say suppose the work function. So are the photoelectrons going to be emitted from the surface of the metal or not? And if they are going to get emitted,
Yes.
what will be the kinetic energy of the photoelectron? So what do you mean by work function of a metal surface?
Threshold.
Work function is the minimum energy expenditure which is needed to remove the electron. Got it? This is the minimum energy which is required. Is it clear or not?
Yes.
So suppose if we are working somewhere in some other city or right, so we are getting some salary. Is the total salary what we are getting? Are we saving that total salary? Total?
No.
No. So where the total salary is, so how much we are saving? Is the total amount salary which we are saving? No. We are saving the salary. We will do some deductions and the expenditure. Got it? And the remaining will be saved. Are you getting my point or not?
Yes, sir.
So similarly, you have the energy of the photon, right? And there will be some energy required to pull out that electron. That was the expenditure. Got it? So how much energy of what is the energy of the incident photon? What is the energy of the incident photon? That is h into frequency of the photon, or h c by lambda. Got it?
Mm.
What I told you in the last class, what is the value of hc?
It's yes.
Hmm.
No.
1240 electron volt nanometer. Okay. I just remember it. It is going to be very easy for you. But be careful that this energy is in electron volt. Right? Divided by lambda. Lambda is how much? 400. And the wavelength should be nanometer. Nm. Got it? Nanometer will get cancelled. Right? It is
Yes.
3.1 electron. So this is the energy of the incident photon. How I found it? It's well. These are the photons which are striking the surface of the metal. And what they are doing? They are ejecting electrons from the surface of the metal. Okay. They are ejecting. So electrons are being ejected. So it is so to do these electrons carry the whole amount of energy which is supplied by the photons. Each photon is coming and striking the electron and it is kicking out the electron from the surface of the metal. Are you getting your point or not?
Yes.
So what will be the kinetic energy of the electron? Total energy of the electron? Will it be 3.1 electron volt? More than 3.1? Less than 3.1?
Less.
Less than 3.1. It is just like the salary which we are getting, that is not the total savings. Okay. We need to do some expenditure for our living, right? There are some daily expenditures. We need to subtract those. So what are those expenditures? So here also, whatever the energy which we are receiving from the photon that is not getting completely transferred to the electron. Some of the energy is being used to pull out that electron, and remaining extra energy is converted to the kinetic energy. So kinetic energy of the electron is 3.1 minus how much? What is that? What is the expenditure? That is known as work function. Okay, 3.1 minus 3 electron volt. Got it? So the kinetic energy is 0.1 electron volt. Are you getting my point or not, Nabila? Tell me quickly. Is this clear?
Yes. Yes, sir.
If anything is not clear, you can ask me 100 of times, right? Don't worry about it, right? You can
Yes.
ask me anytime, anything, right? Don't worry that what I will think, or you can just ask me that this you have not understood. I will explain again in a different way, okay? So 3.1 is the energy of the photoelectron, and this is the work function. Work function is the minimum energy which is required to remove the electron from the surface of the metal. Take the difference, so that is that extra energy, and that will be the kinetic energy of the electron. Is it clear? It is just like a ball. Okay, if I just touch it very slightly with my finger, it will not move. To move it, I need to put some force, certain minimum force. That minimum force is known as work function. Okay, for metals. And if I put more force, that ball will move with more energy. Okay. So when the photon carries just the energy, when the photons what is going on in the school right now? So when you put energy exactly equal to the, if or I can write it in this way, if h nu energy of photon is equal to work function, the electrons are emitted but with the kinetic energy equal to zero. Is it clear? If the energy
Yes.
of the photons is greater than the work function, this work function is phi naught, not phi. So the kinetic energy, more energy you are putting, so you need to take a difference, some extra energy is left. There will be some kinetic energy will be there for the electron. And if the energy of the photon h nu, which is calculated by h into h lambda or h nu, is less than the work function, then the electrons will not come out. If they are not going to come out, the kinetic energy is going to be zero. Photo electrons will be emitted. Here also photoelectrons will be emitted. There will be no emission. Got it? Okay.
Yes.
So this is the graph of the kinetic energy. And the frequency of the light used of the photon. So frequency if you put lower frequency, no emission will be observed. Is that clear? But no emission, no kinetic energy.
Mm.
Once you put the energy equal to the work function, electron will start emitting. And if you put more energy, then the kinetic energy is going to remove. Then it will increase. Got it? If you increase the intensity,
Yes.
increase in intensity, will it increase the number of photons emit? Will it increase the number of electrons emitted, or will it change the kinetic energy of the electrons? What do you mean by intensity of light?
Power.
Yeah, power, just in terms of number of photons you can correlate. More bright yellow light and less bright yellow light, dull yellow light. So how it differ?
Brighter is with higher intensity.
Brighter will have same photons, but more number of photons are coming. Okay, the energy will be same. Dim light or the less bright light, faint light will have less number of photons, but the energy of the photons remains same. So kinetic energy of the photons emitted will be independent of the intensity of the light use. Because intensity will not change the energy of the photon, just more photons are coming, so more electrons are getting released, but the energy is going to be same, it is not going to be different. Is it clear?
Yes, sir.
So now let's move on to the next very important part of the particle nature of light. Okay, that is uh, the line spectrum of an atom. Is it clear? The line spectrum of an atom. What do you mean by line spectrum of an atom? What is spectrum of atom?
The band, the
Yeah,
colors.
yeah, the colors emitted by the atom. So, and they are not the continuous like rainbow, right? Line spectrum of atoms or spectrum of an atom. So, spectrum of an atom, you can divide it in number of ways. There is continuous spectrum. Okay, like visible region of light. You can find the spectrum not by naked eyes, but you can detect it when you pass the light through prism. You see a rainbow, but that is continuous spectrum. And suppose if you have a discontinuous spectrum, okay, Spectrum is the whole array of light or the wavelengths which are released by atoms or molecule. Atomic spectrum. Okay, then you have molecular spectrum also. This atomic spectrum is line spectrum. Molecular spectrum is band spectrum. Suppose if you observe a light, uh, uh, first you need to heat the gas, okay, or the sample which you need to give it some energy of through which you are, or you should put it in some light, so that will absorb certain amount of energy and it will release. So if you analyze the energy which is being released by the molecules, you will observe the bands like this. This is known as band spectrum of an atom. Is it clear?
Yes.
And at this is, you see regions like this, bands, okay, in molecules. Remember this, in atoms you see the line spectrum. I've shown you the diagrams. Okay, so line spectrum. This could be absorption spectrum or emission spectrum. Got it?
Yes.
Okay. Absorption spectrum is when you put the light on a sample of gas, it absorbs, and there you will see the some lines are missing, and you will see a dark space. It is just like suppose a comb you take, okay, and you put a torch light on it. What happened to the other side of the light passing through the comb? You see there are some dark lines, the shadow of the comb, right? So that light is being absorbed by the comb. Similarly, for an atom, you put some light, it absorbs certain wavelengths. Not all wavelengths are, okay. This is discontinuous. Okay, not all wavelengths are absorbed. And when you keep that sample for a certain period of time, it is again going to release those wavelengths back, and you will see them as colors. Got the point or not? Is it clear?
Mm.
So emission spectrum and absorption spectrum are just one and same thing. Okay. The main thing is they are considered to be the fingerprint of an atom. Okay. And they are discontinuous. Means atom can absorb certain wavelengths and emit certain wavelengths, but not all wavelengths can be absorbed or emitted. Got it? So now we will we will discuss the line spectrum of an hydrogen atom. Line spectrum of an hydrogen atom. You know why they are called line spectrum, that I already explained you. Okay, there were certain colored lines which you see when you put the hydrogen sample. So suppose this is some hydrogen sample which you have taken and you put it in some electric or magnetic field. Okay, this is known as excited sample, right? And it releases certain energy. Excited sample, it releases energy, right? Some energy we cannot see with the naked eyes. So what we need to do, we need to take a prism. Okay, and when they are passed through prism, there is a screen which is put on the other side of the prism, and you see that not all the wavelengths like the rainbow are observed. Just few lines, colored lines are observed. Is it clear?
Yes, sir.
This is known as line spectrum of an atom. If this is emission spectrum because it is analyzing the light which is emitted by the hydrogen gas. Okay, so the people were interested to know why the atom is releasing only certain wavelengths as lines. The certain colors, only certain colors are being emitted. That's why you see only particular colored lines. All colors are not released by the atoms. What is the reason? And can we correlate the wavelengths which are released by a sample of gas? Okay, is there any formula, numerical formula by which we can figure out what are the wavelengths which can be released? So we are going to discuss line spectrum of hydrogen atom. Okay, and whatever the wavelengths which were being released, people analyzed that those wavelengths are because of the transition of electrons within the hydrogen atom. Okay, and they have found the formula also, 1 upon lambda equal to formula to get the wavelength of those lines or the colors which are being released by the hydrogen atom. And this for the formula, wave number or 1 upon lambda equal to r, 1 upon n1 square minus 1 upon n2 square. N2 is greater than n1. This formula they found. So the wavelengths of the line or the colors which we are seeing, the wavelengths can be calculated by this formula. What is R?
The constant.
Yeah, it is known as Rydberg's constant. One zero nine six double seven per centimeter, because it should have unit of 1 upon lambda or per centimeter. Got it? Is it clear?
Yes. Yes.
So And what is N1 and N2? Okay. So N1, if N1 is 1, N2 is any higher whole number, 2, 3, 4, 5, and so on. And this group of wavelengths or the colors which are emitted, they come under the category of Lyman series. Lyman series of wavelength. These wavelengths are not visible to us by a naked eye, but in a spectrophotometer they can be detected. Is it clear? By the instruments we can detect them,
Yes, sir.
and they come under the UV region because our naked eyes cannot, but they are present. Okay, but we cannot see them in the by the naked eyes. Is it clear or not?
Yes,
Lyman
sir.
series of wavelength, okay, is actually Lyman series is observed if you try to look at the hydrogen atom. This is what is happening. Okay, if we try to understand in terms of pure maths, it is very difficult to understand that what these numbers are and what they mean. But if we try to look at it in terms of from the point of view of an atom, okay, I can easily make out what is Lyman series. So suppose this is an atom, this is a nucleus. Okay, and these are various orbits, got it, in an atom. Okay, the electron can be, what happens when you give some energy, when you heat, the electron jumps from lower orbit to higher orbit, which is having more energy. Okay, and the electron fall back into its lower orbit. So suppose if it fall back to the first orbit from any higher orbit, got it? This is which orbit? This is 1, 2, 3, 4, 5. So if the electron come from 5 to 1, it is going to release a Lyman series of wavelength, or 6 to 1, 7 to 1, seventh orbit to first orbit. It is, suppose if the electron come down to the second orbit, it's not necessary that the electron from the higher outer orbit, okay, will get back to the first orbit. It can get stop at the second orbit also. So if the electron make transition from third, fourth, fifth, sixth orbit to the second orbit, okay, this is these were showing Lyman series when the electron is making transition to the first orbit. If the electron is making transition to the second orbit, I can use different color so that you can easily see. This is the first orbit, this is the second orbit. And if the electron is coming to the second orbit from any higher orbit, what happens? Electron is losing energy and it will release certain wavelengths. When 3 to 2, or from fourth orbit to the second orbit it is coming, These wavelengths come under the category of Balmer series. Is it clear? And they are visible
Yes.
to us. So how the electron move to the higher orbit? What's the reason? Why the electron move to the higher orbit? It will move to the higher orbit because we may have heated the atom and we have given some energy, so the electron may jump to some higher orbit. And when it is kept for some time, the electron get back to its original orbit and it releases its energy back. Depending upon the orbit which to which the electron come down, the accordingly the energy is released or the wavelength is released, and these wavelengths are segregated together under different names and sections. Okay, and the Lyman series consists of those wavelengths when the electron from higher orbit come down to the lower orbit. Balmer series, electron from the higher orbit come down to the second orbit, and this is very important because these wavelengths are visible to us. They are in the visible region. Are you getting my point?
Yes.
Okay, and this is the formula which you can use to calculate the wavelength. Got it? I will show you the calculation also. Suppose if the electron is moving in some higher orbit, it has moved to some outer orbit due to giving of by absorbing some energy, and after some time, if the electron fall back to the lower third orbit, it is known as, so it will release some energy or photon of certain energy, or which will be appeared to us as some radiation or some wave light. Okay, and that comes under the Paschen series. Okay, so Paschen series constitutes those wavelengths which are released when the electron jumps from the higher orbit to the lower orbit. Okay, Lyman, Balmer, Paschen. Then you have bracket series of wavelength. This happens when the electron come down from fifth, sixth, seventh, eighth to the fourth orbit. Fund series, when the electron jumps from sixth, seventh, eighth, ninth, or any higher orbit to the fifth orbit. And Humphrey series of wavelength. So actually these, whatever the line spectrum were there, their wavelengths were grouped together. Got it? They were grouped together. How they were grouped together? They were grouped together on the basis of how the electron from which higher orbit the electron is getting down to which orbit. Okay, and releasing what wavelength. Humphrey series of wavelength constitute those wavelengths when the electron jumps from any seventh, eighth, ninth. So we can't stop the electron. It can, from suppose that the electron is moving in the 10th orbit and it will lose some energy and it will get back to ninth orbit, or if it get back to sixth orbit from any higher orbit, that will release the wavelength that is named under Humphrey series. all these wavelengths, they are also not visible to us. They are infrared. Okay, only the Balmer series wavelengths are visible to us. Are you getting my point or not?
Yes, sir.
Only the Balmer series wavelengths are visible to us. So whatever the line is spectrum, whatever the wavelengths are there, okay, they are segregated together. They are grouped together by the movement of electron. These wavelengths are released when electron moves from higher orbit to lower orbit. It loses its energy, and that energy is released by an atom in terms of wavelength. And depending upon how it moves from higher to lower orbit. Got it? It is these wavelengths are named. So Lyman series, when the electron moves from higher orbit to first orbit. Palmer series, higher orbit to second orbit. Got it? So a lot of these questions are asked in NEET
Yes,
also,
sir.
right? So how will you calculate the formula of the values of this wavelength? Okay, you are going to use the above formula. What was the formula for calculation of these wavelength? 1 upon lambda equal to R. What is 1 upon n1 square minus 1 upon n2 square. This is how you can calculate the formula or the value of the wavelength. Is it clear? What is the value of R? What is R known as? R is known as Rydberg's
Right.
constant. Got it? Rydberg's constant. So you can put that value, and the question will tell you that if the electron uh, is um, is making a transition from this orbit to this orbit, okay, you are going to put the value of the orbit numbers. Is it clear? And you are going to get
Yes,
the
sir.
wavelength, right? So let's say find the wavelength of the first line of the Balmer series. So what it means actually, first line of Balmer series. Balmer series is the series of wavelengths which are released. These wavelengths are also known as lines. Okay, when the electron moves from higher orbit to second orbit. Okay, when the
Okay,
electron
sir.
jumps from any higher orbit to the second orbit. Is it clear? So the
Yes.
first line is the first jump. So when the electron just jump from n equal to third shell, okay, to second shell. This is known as first line. Just the adjacent. If the electron changes just one or step of one orbit, adjacent orbit. First line of the Lyman series when the electron jumps from second to first. What is the first line of bracket series? What transition represent the first line of bracket series? Can you tell me, Nabila?
So
First line of the bracket series. What transition represent bracket series? First line, the first wavelength which is released by the which comes under the bracket series under the name of bracket series. It happens when the electron jumps from the fifth orbit to fourth orbit. This is the first line. This is the second line. Okay. This is the third line. Okay. Is it clear or not? This is how it is called.
yes.
But you need to know the names and you need to know the final orbit in which, according to the name, for each corresponding name, there is a final orbit to which the electron get finally jumped, okay, to that final orbit, and accordingly you will have the uh, wavelengths calculated. Okay, so Lyman's Balmer series. What is the Balmer series first line? You understood? So 1 upon lambda equal to r. What should I put in place of n1 and n2? You should 1 upon n1 square minus n2 square. Okay, so 1 upon 2 square, always bigger number you should put after the minus. Got it? Is it clear? So what is the value of lambda? In terms of r, it is how much? R 9 minus 4 is 5 and 36. Is it clear? So what is the wavelength of the first line of the Balmer series? Lambda equal to 36 by 5 r. Is that clear or not?
Yes, sir.
It is 36 by 5 r. What is the value of r? Either you can put the r. What was the value of r? 109677 per centimeter. Is it clear?
Yes.
So R, I can simplify it for you. R equal to 109677 per centimeter. Okay, means because it is wave 1 upon wavelength. Okay, so that's why R is having the unit of per centimeter. So if I write this is per meter, got it? 1 centimeter, I can change it to meter. Per meter. Is it clear? Or just remember this value. No need to, for you don't have to, you don't have to do the calculations. I will tell you the final value which you need to remember. This you can remember. Got it? This is the final value which you can remember. Is it clear or not? No need to for you to
Yes,
calculate.
sir.
Why I am telling you the value of 1 upon r? What's the reason?
It's easier to calculate. How to calculate.
I am telling you the value of 1 upon r because when you calculate the lambda, you will do the reciprocal. And the r, which is a numerator, that will come in the denominator. So you directly, if you put the value of 1 by r, it will be easier for you to have the calculations completed. Okay. So this is lambda equal to 36 by 5. 1 upon r is 911 or 912 angstrom. Is it clear? This you can remember.
Yes.
912, 911.6 it is actually. One upon r directly you can put the value and you can get the wavelength. Let me calculate it for you. It is actually 911.6. Okay, so I'm taking it as 912. So 36 into 912 divided by 5. Right? So it is going to be 656 angstrom. Or lambda is 656.6. Angstrom is 10 to the power minus 9 meter, 10 to the power minus 10 meter, and this is 10 to the power minus 9 meter nanometer. This is going to be the value of lambda.
Okay, sir.
Okay. Can you calculate the wavelength of the first line of the Lyman series? These questions, lot of questions are being asked in NEET. Okay. Calculate the wavelength in nanometers of first line of Lyman series. Just tell me how you are going to calculate. Lyman, Balmer, Paschen, bracket, P1, right, and Humphrey. So Lyman series was the first one where it happens when it is so when the electron jumps from any higher orbit to the first orbit. Yeah, tell me now. And the first line of Lyman series. How should I calculate the wavelength for hydrogen atom?
From 2 to 1. From 3
1
to
upon
1.
lambda equal to r, right? 1 upon n1 square minus 1 upon n2 square. This is the formula I'm going to write. What do you mean by first line? Which transition of electrons in hydrogen atom represent the first line of Lyman series? When the electron moves from which orbit to which orbit?
To first orbit.
From second to first orbit. Noted Lyman series was the first series of lines of first orbit, and first line of the first series is second to one transition. So what is the wavelength? Lambda equal to r 1 upon 1 square minus 1 upon 2 square. Okay, so this is going to be 1 minus 1 by 4. 3r by 4. Got it? Is it clear? So what is the value of lambda? 4/3, 1 upon r. Instead of doing that per centimeter and all, I told you to put the direct value of 1 by r. That was how much? 912 angstrom. Okay, 911.6. Actually, it was 911.6. So I took it as 912 angstrom, right?
Yes,
So
sir.
4/3 into 912 angstrom. Got it?
Mm.
So how much it will be? 1216 angstrom, right? So it is going to be 121 angstrom with 10 to the power minus 10.6 nanometer. Is it clear?
Yes, sir.
We will do one more question, then we are going to move ahead to the Bohr model. So actually, scientists were why these lines are emitted. Okay, because it happens because when you give energy, the electron absorb that energy, photon, and it moves to the higher orbit. Okay, and it get back to the lower orbit. It release that energy back. Depending upon the lower orbit in which the electron enter, you will have wavelength being released. Okay, and that wavelengths, depending upon the number of the lower orbit, are grouped together under certain names: Lyman series, Balmer series, Paschen series, Brackett series, Fund series, and Humphrey series. Out of all these grouping of wavelengths, only the Balmer series, initial line of the Balmer series are visible, where the electron jumps from higher orbit to the second orbit. The first line represent the two adjacent jump between the two adjacent orbits. Okay, and the limiting line or the last line is the jump from the last orbit or infinity to that particular orbit of that particular series. Okay, so if I ask you calculate, till now I was asking you only to calculate the wavelength of the first line. Calculate the wavelength of limiting line is the last line of the Balmer series. So how you will calculate? The formula for all of them is same. 1 upon lambda equal to r 1 upon n1 square and what does this Balmer series represent and what does this limiting line of the Balmer series represent? Tell me quickly.
Infinity.
It is r. Balmer series represent the transition from higher orbit to which orbit? First orbit, second
Lower,
orbit, third orbit. Which one? You need
third, second.
second orbit. Lyman, Balmer, Paschen, Brackett, Pfund. Okay. So Balmer series correspond to the jump of electron from higher orbit to second orbit. Got it? Is it clear?
Yes, sir.
And the because the electron is going to lose the energy, the wavelength which is being released 1 upon lambda equal to r 1 upon 2 square. And this is asking about the limiting line. Limiting line is the last line, which is the last shell number. Do we know that?
Infinity.
Shell number can be anything, 3, 4, 5, infinity, or a very big shell number. Okay, infinity means that. Okay, so I'm going to put limiting lines means transition from infinity to that particular orbit about which it is asking. Right? Is it clear?
Yes, sir. Yes, sir.
So this is a very big number. 1 upon big number is 0. Square of big number is further bigger, and 1 upon very big number is a very small number. Okay, like 1 upon
Mm.
1000, 1 upon 10,000, 1 upon 1 lakh, 10 lakh, right? It is going to be close to 0. I'm going to take it as 0. And this is 1 upon. So lambda equal to 4 by r. What is the value of r in angst? 1 upon r. Either you put the value of r. If you put the value of r, actual value of r, you have to divide. And because the division is difficult, so I directly told you the value, put the value of 1 by r.
Yes, sir.
Okay. If you take the value of 1 by r, remember the value of 1 by r. You can easily get through this calculation.
913.
4 and 911.6. Or if it is or 91.16 nanometer also you can use. Normally these are expressed in nanometer, right? So how much it
Yes,
is?
sir.
16 fours are 64, 4 ones are 4, 9 fours are 364.64 nanometer. It will lie
Okay, sir.
under the UV region, because our naked eyes can see the wavelength from 400 nanometer to 750 nanometer. Okay, smaller than this is UV. Higher than this wavelength. This is the wavelength range which is visible to us. Okay, lambda. And this is infrared. So Lyman series are very famous because they are close to visible region. Okay. Is it clear? Now the next question.
Yes,
This
sir.
question is very simple, and most of the examinations have this kind of questions. Okay, you will see lot of question in NEET, mains, JEE, CBSE, or everywhere, and they are very easy, but you have to be very careful. Find the ratio of wavelengths of ratio of wavelengths you have to find of the first line of Lyman series to the second line of Balmer series.
Yeah.
So 1 upon lambda equal to 1 upon r. Lyman-Balmer pass. First line is one transition from 2 to 1. Okay, this is going to be, this is 1 upon lambda, not lambda. This is the wave number. Okay, wave number of if you don't calculate lambda, it is the wave number. If you calculate lambda, that is the wavelength. Wave number, I told you that it is represented by nu bar. Okay, and it is going to be 1 upon r. 1 minus 1 by 4, that is 3 by 4. Got it?
Yes, sir.
You have to find the ratio of wavelength. So lambda is equal to, this is lambda 1, call it lambda 1 equal to 4r by 3. Let me move to the next one. 1 upon lambda equal to, what is the second line which the question is talking about? It is the second line of the Balmer series. So Balmer series is when the electron jumps from higher orbit to the second orbit. So first line of the Balmer is 3 to 2. Okay, second line is from 4 to 2. Balmer series comes when the electron jump from higher orbit to second orbit. So third to second is the first, fourth to second is the second line of the Balmer series. Got it? So it is going to be how much? 16 minus 4, that is 12 by 4 into 16, right? Is it clear?
Yes, sir.
So it is, so lambda 2 is going to be, just let me simplify it, 3. Lambda 2 is going to be 16 r by 3. When they are asking you to get the ratio of the wavelengths, you don't have to put the value of r because that is going to get cancelled. The ratio is lambda 1 is to lambda 2, okay, and 4r by 3 is to 16r by 3. Got it?
Yes, sir.
So r by 3 will get cancelled. It is 1 is to 4. Is it clear?
Yes, sir.
So that's how you're going to get the. So what these indicated? These indicated that the electron is moving in certain orbits, and when it absorbs energy, it it absorbs energy. It jumps from lower orbit to higher orbit. Okay, outer orbit, and that is that wavelength which is absorbed. You see that wavelength missing from the visible region because that is being absorbed by the electron. And when the
Yes.
electron get back to that original orbit, it releases the wavelength back. And when it releases, okay, that line is visible to us. But if the electron is in the sixth orbit, it has multiple options. It can come down to the fifth orbit. Okay, if it's from sixth, it is coming to fifth orbit. That will be the first line of the Pvt series. If the electron is in sixth orbit, it can directly jump to the fourth orbit. That will be the bracket series. Okay, if it is from the sixth orbit, it is getting to first orbit. That is the Lyman series. Okay, so that's how the various wavelengths emitted from hydrogen atom were grouped together. Their formula was derived. Okay, and their wavelengths could be derived And now we know the first line is just the transfer of electron taking place between the two adjacent energy levels. And the limiting line is when the electron moves from infinity to the first one or the second orbit or the third orbit, depending upon the series which we are talking about. Okay, so now we will calculate the formula for other atom. This is for hydrogen atom. Okay, for other atoms the formula is very simple. For other hydrogen like uni-electronic species, the formula becomes a hydrogen like uni-electronic species is, for example, hydrogen is having one electron. Helium is having two electrons, so you remove one electron, so He plus will be having one electron. Then lithium plus two is having, lithium is having three electrons, so this formula is applicable to one electron. You need to remove two electrons, so Li plus two, Li plus two, because you have removed two electrons. Beryllium is having four electron. If this formula is applicable for single electronic species, so you need to remove three electrons. Okay, so beryllium plus three. So this formula is applicable to calculate the wavelength of the line spectrum emitted by various other single electronic atoms or ions, uni-electronic species. Is that clear or not?
Yes, sir.
So, but you need to put the z square, that is the atomic number. Okay. For lithium,
Okay,
it
sir.
is 9. Okay. So all this thing, let us think that electron is moving in certain orbits. And Bohr actually concluded its model based on the observation made from the line spectrum of an atom. Is it clear? So the line spectrum of atom
Yes, sir.
let us to think that the energy of the electron move in a particular orbits. Okay, but Rutherford was not able to tell, because Rutherford was not able to decide, because as per the Rutherford, the electron should fall into the nucleus. That was not, Rutherford was not able to explain the stability of atom. But in this case, we are seeing that the electrons are moving in certain orbit, and they absorb energy when they move from inner orbit to outer orbit, and they release energy when they move from outer orbit to inner orbit. When they move from outer to inner orbit, lower orbit, they release energy. Okay, and those energies are visible to us in the form of line spectrum. Okay, because only certain particular wavelengths are released. Got it?